So good morning, everyone. I should say, excuse me, good morning, good afternoon, and good evening, everyone. Today, Richard and I are going to be facilitating discussion for the first half of the morning, or I should say again, morning, afternoon, and evening, depending on where you are, on the topic of enabling mass spectrometry for radionuclide metrology. We wanted to provide you a little bit of kind of an outline or template, if you will, to get you thinking about this particular topic area.
I'm sorry, Jackie, to interrupt, but could you
Sure.
put your presentation in show mode? Right now we are seeing edit mode.
Oh, I'm sorry. It actually is in show mode for me. Let's see. I will go. I have another thought. Hold on. Okay, let's see. Did that work?
No, so it's fine to do it this way. That's okay. Should be
Interesting.
aware though that it's in edit mode.
Okay, sorry about that. I tried the other direction where you go up from the top of the file, so I'm not. Anyway, so one of the things we wanted to do first was just going to give you a little bit of information to start thinking about and things to chew on for the discussion. And the first is that in this particular area of enabling mass spectrometry for radionuclide metrology, there really are two communities that are interested in this topic. There's the metrology community. So those are the folks that are, the National Metrology Institutes, the designated institutes, other type of metrology institutes out there. Those are the ones that are developing the metrology tools and the techniques that our customers and stakeholders. We deliver those tools and develop those tools for our stakeholders and users. And then there's the analytical community. Those are the folks that are actually using those metrology tools in their daily radionuclide measurements, the routine measurements that they're doing. And both of those communities have some overlapping needs that may be similar in this topic area, but they also have some distinct needs. So the metrology community is going to be probably more interested in primary technique and primary measurement techniques, whereas the analytical community is not as quite as interested in something like that. So for specific discussion areas, we hope to go over today. The first is traceability to the SI, which we did touch on a little bit yesterday when the topic of actually primary reference measurement procedures came up. Also, fundamental data. In this case, this also came up yesterday when we were talking about improvements of half-lives and branching ratios and things like that. Also, reference materials. That also came up yesterday when we were talking about the 3000 series, the spectrometric solution that NIST sells and being used for mass bias, even though they are not certified for isotopics. Infrastructure. There's something that we did not bring up yesterday. In this case, we're talking about kind of the facilities that you may need when you're doing radionuclide measurements by mass spec, meaning glove boxes around your mass spec and things like that. A lot of our actual stakeholders and users kind of have these facilities, but in some cases, believe it or not, some of the NMIs might not have the appropriate facilities for things like that. Then there's techniques. This came up a little bit yesterday. In this case, we're talking about, like, for example, where for mass bias correction, for years, it's been, people typically use something like a linear power exponential correction, but over the years, there have been other types of techniques that have been developed beyond, like, sample standard bracketing. Like, there's sample standard bracketing with an internal standard. There's regression techniques. There's now a K-factor, or what I kind of call the Avogadro approach that PTB has been instrumental in. And then there's the final topic area of, like, routine versus developmental measurements. Different things are going to be needed for things like that. So what we'd like to start with today is traceability to the SI. I'm going to turn it over to Richard. And Richard, I'll just advance the slide to just kind of kick us off. We're talking about the traceability of the SI, and here's some slides that Richard put together that he can describe. So, Richard, I turn it to you.
Well, thanks, Jackie.
Did this slide advance, just so I know?
No, it did not.
Oh, I don't know what is going on.
There it is. There it is.
Interesting. Okay, I got to be out of that mode. All right, go ahead.
Okay, so So again, the goal here isn't for me to sort of talk about traceability to the SI, but sort of get the perspective from this large group of people, many of whom know more than I do and have different perspectives as well. I've just put up a couple of definitions here from the VIM. One for metrological traceability, a property of a measurement result whereby the results can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. And then I've also thrown up the definition for a primary reference measurement procedure. Because, and the reason for this second definition, a reference measurement procedure used to obtain a measurement result without relation to a measurement standard for a quantity of the same kind, is because frequently with mass spectrometry, we can have metrological traceability, but that doesn't necessarily mean we're using a primary reference measurement procedure. I can give an example of where you are, like for some reference materials you're producing, the early NIST U series was made by gravimetric mixing of N members, highly enriched, uranium-235, highly enriched uranium-238, and so it was essentially gravimetry to produce the isotopic ratios that were being sought. So that was sort of a primary procedure for producing an isotopic ratio reference material. But then even later reference materials, and certainly the measurements that were done using these reference materials as calibrants are traceable, but they're no longer sort of primary measurement procedures. And for mass spectrometry, I think, there's a lot of, I don't know, sometimes questions come up about traceability. For instance, using external calibrants is, as Jackie mentioned, sort of sample standard bracketing, which is primarily what's done for thermal ionization mass spectrometry analysis. Although, as was mentioned yesterday, there's other techniques like total evaporation and modified total evaporation, which try to minimize the need for a correction, but they don't necessarily eliminate it. There's still some remnant bias in these measurements frequently. So I mean, like I said, rather than me talking, I'd really love to get the perspective for the group. Or are there particular concerns or insights that folks have into traceability for the kind of measurements we want to do for radionuclide metrology, which can sometimes be straightforward isotope ratio measurements for some systems where you have multiple radioisotopes of essentially radionuclides of the same element, true isotopes. In other cases, when you're doing IDMS to get an amount for a half-life measurement. Again, these are some of the things that I think about in the terms of traceability. And one last comment is something that we run into frequently, and Jackie touched on this earlier with like the 3000 series SRMs, where people are using a reference material that was essentially for chemical assay, specifically for things like ICP, OES, and but we're using it as a tracer, or not a tracer, as a reference material for doing isotopic analysis of an element, or even using it as reverse spikes for determining amounts of nuclides. We'd be doing frequently, what we're using is like a UPAC value ranges for values and uncertainties for these materials. is that sort of traceable? These materials have not really been checked against those values, although a lot of people who do the analysis look to see that it's at least consistent with what's expected. I mean, is this a place where traceability breaks down? So I don't know. I guess I'm sort of looking for any thoughts or comments from the audience. For instance, is there a has there ever been like an executive decision that using sort of IUPAC values and the associated natural ranges, is that appropriate for traceable measurements?
Richard, do you want me to go to the
Raphael
next?
has his hand up.
Yeah.
Oh, okay, go ahead.
So maybe my ignorant questions or points here might generate some discussion. First of all, I think when the issue of primary reference measurement procedure, I know the definition quite well. I also know, when I first started in metrology, it was primary and secondary measurement methods. I thought, obviously, primary is better. But at the end of the day, as long as using a secondary or a reference material, as long as the traceability chain is there, that's what's critical. So I think it's always important to remember that as well. In radionuclide metrology, oftentimes we call something primary, and when we have tracer methods, we call that primary, but it explicitly has a measurement of the same kind, of another isotope of the same. So there is some aspect on judgment from the different CCs as to what is considered a primary. But again, at the end of the day, that's not the critical point. With respect to the IUPAC values, and here I have no idea. I understand that you look up the natural abundance of these things, but different uranium deposits in different parts of the world can vary. So the question I have is, if you have a certain type of a CRM or natural uranium, does the certificate, you evaluate those, you measure those in your particular sample, are those IUPAC values declared on the certificate, or are the measured values put on the certificate? And if you are using IUPAC values, does that give you a large range to cover all the possible variations of uranium materials?
So I think that's really some good points, and I sort of get what you're getting at, but actually uranium and plutonium are sort of special cases, since there are existing synthetic calibration mixes. So there's a case where you really don't need to rely on IUPAC values if you don't want to. But for most other elements, a lot of times what people are doing is they're taking what they assume to be natural, use the IUPAC values, which they give sort of a best measurement, but they also give sort of the observed range. And that's generally, whenever I go to that, I generally use that observed range value as an uncertainty on the value I'm using. So I guess that sort of covers the natural variation, or even some measurement variation from the various people who've looked at these things.
But if you have a certified reference material and one that is not well understood, don't you measure that? Don't you put the abundance ratios or the isotope ratios in that sample that you're offering as a CRM?
Well, usually if I'm in a situation where I might be missing. Do you understand?
Is it measured? Is it something that you measure when you're evaluating a CRM?
Yes, I think to answer that question is yes. I mean, the only time that IUPAC values have been assumed for composition is so when it's a situation where there is no isotopic reference material available. So NIST also back in the 60s and 70s produced a 900 series, 986, 976. They're like copper isotope standards, strontium isotope standards. A lot of those have run out. So they've moved on to using the 3000 series. Now the 3000 series is not certified for isotopics. The 900 series was. So when you have something, when you just don't have anything available for mass bias correction is when people are using the 3000 series, which are not certified for isotopics. So what they typically do is use the IUPAC values for what the natural composition of whatever that material is. They do also measure it, but you still don't know. You don't have like quote unquote certified value because nobody's actually measured it in a rigorous way. So they still use the IUPAC values. I don't know if that's answering your question.
Yeah, I think Zoltan may be chiming in here. I don't know if it's a question,
Okay.
but
Yeah.
thank you.
But before Zoltan, I call on you. I would just observe that Richard made an interesting statement. I think there are many cases, even in radionuclide metrology, where an executive decision has been taken as to what we will consider primary. I'm thinking specifically of the tracer methods used in liquid scintillation counting. If you were to take the primary definition according to the VIM literally, it would be, well, I could justify why it's primary despite the fact that you're using another radionuclide, but it's not obvious from the outset. So the consultative committees in all technical areas do have the flexibility to be able to define something as primary as long as it follows the spirit of the VIM definition. So with that, Zoltan. Oh, I saw that Michael also put up his hand. So Zoltan first and then Michael.
Sure, excellent discussion. So I just would like to add one consideration in the traceability concept, along thinking this chain concept that measurements or calibrations are linked back to some initial point. Along with that concept, we also have to constantly carry the uncertainty concept. So the question is, what is a useful uncertainty, and whether that chain concept of linking back to a primary calibrant is maintained within the uncertainty realm. What is useful for the end user. So Richard was saying that almost all chemical measurements are, and especially mass spectrometry is a non-primary method, so we need physical calibrants to realize measurements, and that's absolutely correct in the useful uncertainty regime where chemistry operates. However, there are mass spectrometry approaches for both isotopes and mole or mass fractions, which are primary. You can do direct measurements with very large uncertainties, which require no external no calibration input. So it would be, I was asking this question also yesterday, it would be important to understand the uncertainty needs where the radiometric measurements and community operates, because for some of those uncertainties, if I understand correctly, some of our mass spectrometry methods are pretty close to providing direct estimates. So on evaluated isotope data and IUPAC, I would just add one concept. It was all correct and all well described before. So IUPAC is representing, that's an evaluated data set on isotopics, and this represents the natural evaluation. If the question, what the users are posing, that where your sample is in with this natural distribution space, isotopic profile distribution, then you cannot calibrate against the average distribution on Earth, obviously, because the uncertainty, the spread on that would be just simply too large. And as we referenced this yesterday, many of the isotope measurements in these cases are actually referencing to an artifact. Those are the standards what Jackie described as the mass fraction or mole fraction standards from NIST, which are used for some other purpose, but they represent the physical material which is available to everybody, and the communities often use those materials as secondary or off-label use to normalize their isotope measurement against and reference against those samples, with all the caveats which was described, that when once a new series released, that might be not the same point. So yeah, so carry the uncertainty concept all along, and it would be important to understand where the radiometric measurements are in uncertainty need versus let's say the stable isotope ratio measurements with mass spec, and also the mass fraction measurements with mass spec. Thank you.
Thank you, Zoltan. Before I move the mic to Mike, Mark Tyra has put a comment in the chat with isotope dilution mass spec. You are using gravimetric measurements for your reference materials and for mixing reference materials and samples, but measuring ratios. So there are, in effect, two items, not just like and like. I think this is part of the argument that IDMS is a primary method. And with that, Michael Winchester and then Robert.
Actually, Mark sort of stole what I was going to say, but let me say it a different way. At least in the CCQM space, back in, I probably don't have the date right, but in the late 90s or so, maybe the early 2000s, I think it was the late 90s, the CCQM defined primary method and actually distinguished between two different types, primary direct and primary ratio. And the one that fits the now VIM definition of primary reference measurement procedure is the primary direct, what we call primary direct. So, for in the chemistry space, things like coulometry, where you're measuring a quantity of substance, but the traceability goes back through the second and through an electrical parameter. So it's calibrations through something of a different type. But IDMS, for example, we think of that as a primary ratio method, where you are using a reference material that has assigned values of the same type that you're measuring, but that traceability goes on back farther, as Richard was saying earlier, hopefully to a primary direct method at some point. Chemistry is very complicated with the traceability routes, and sometimes it's hard to actually, want to know the truth, sometimes it's hard to figure out what the traceability route really is. But that's what we try to do. So as Lisa said earlier, the CCs do have the flexibility to define other terms, and that's what we've done in CCQM. And even though the VIM has been around, the VIM 3 has been around now for a number of years, we still tend to think of both primary direct and primary ratio methods, where the definition really is that the measurement is completely understood, can be written down in an equation where the parameters are all in SI units. And, we still make good use of that.
Yeah, I think it's really important to keep in mind that metrology existed before the VIM made any of these definitions. So as metrologists, we have been having to define what primary is for many more years than yeah.
And one just little follow up to that, and then I'll let somebody else, let Robert, I guess, was next. But yeah, I mean, the chemists tend to not pay as much attention to the VIM.
Don't say that in public.
We do to some degree, but we don't. I know Robert's wincing in his chair there. But,
yeah, he's next, and then Jackie.
I think we don't tend to pay as much attention to it, maybe as some other communities do. Go ahead, Robert.
Well, my philosophy has always been the VIM should serve metrologists, not the other way around. So Robert, you're next, and then Jackie.
Mike, what sacrilege, what sacrilege. Anyway, what I wanted to say is I think one of the things, obviously in the CCQM, so I'm from the CCQM side, we obviously had long discussions about primary methods. But one thing that's happened, and I don't know if you do this, is, and Mike alluded to it, actually, when we set up a calibration hierarchy for chemical measurements, we usually pass through various stages from a procedure to a material to another procedure to another material. And actually drawing these calibration hierarchies has become very, very useful. It's really where we've progressed to, because if you, for example, want to measure something in a complex matrix, you probably need to use a different procedure than you would higher up the calibration and hierarchy, and so on and so forth. And then you know, primary, secondary, you start running into problems because you can have primary reference materials, primary calibrators, secondary calibrators. They're not so important as actually knowing which methods and materials you're using and how the uncertainty goes. And then we have other issues like, does your reference material really act like your sample you're measuring? Is it commutable, et cetera, et cetera? So, but we have some nice examples of those sorts of things that we could share with you. It really comes from the clinical chemistry space, where you have to provide a well-defined calibration hierarchy to the IVD industry, which they're waiting for. And we've sort of developed that in other areas. It's really quite a nice way of looking at these things, and it avoids too much discussion on, is it really a primary method? Well, is it really achieving the uncertainty you want with the correct material at the right level? That's where we're at, really. Thank you.
Great, thank you. Jackie?
I'm just agreeing with what Robert just said. And also, I think to put it in like a shorter version is just, is it fit for purpose for whoever the end user is? And bringing back Ken in, you know, he was always like, is it fit for purpose? In some cases, there are communities out there that might not need traceability to the SI. I know that sounds bad, but it's true. They might need just traceability to an SRM. So it's important, I think, to realize who the end users are and what they need. And there are cases where there's a clear need for traceability to the SI, but not always. So.
Yes, something that's particular in the ionizing radiation side of the shop is that regulators, so people who really know nothing about measurement of ionizing radiation, regulators often pick on buzzwords like what you will find in the VIM to say in their regulations, well, you know, you must be traceable to the SI, even though we as metrologists or we as analytical users, we're not necessarily thinking about that as the key point of the measurement. So when we think about the stakeholder community on the ionizing radiation side, this issue of traceability to the SI becomes, and primary methods and primary measurements to get there become more of an anxiety issue. We can tell them the Consultative Committee on Ionizing Radiation has determined that this is traceable or this is primary. Regulators don't always know that.